I agree with geometry.
I tried
Keep the probability, and then the only one that doesn't have a color that matches.
I see what you're doing.
It's time for us to get started, so I'm glad to see the 7 of you here that are here. We're missing Alice today, and she asked that we videotape it just in case, she can view it, so that she can view it later. The first thing that I want to start off with, and we spend just a little time asking, first of all, did you get your homeworks back?
Yes.
The second question, do you have any questions about the way they were graded? It's okay to ask anything you want. Anyone with any questions about it?
Yeah. Same.
Okay. Well, I'm glad that it's clear how the homework was graded, and the scores were good. I'm going to, I think, maintain the grading scale. That was something that I didn't say anything about during our first meeting, but if you look at the syllabus, we have some room, if you will, in order to to get an A. And I'm going to maintain that, and all the papers were very good in terms of beating the A range. And we have a new homework assignment that I think I've assigned for it to be due on Wednesday. And today I wanted to open up the floor, a good portion of the class period, to ask if somebody wants to see something similar to the homework, or has a particular question for part of the homework problem that they'd like for me to address. Anybody want to ask anything about homework too?
I guess I have some general questions that pertain, I guess, to a little bit of this homework about the limits of integration, how you choose those.
Okay.
So if you could talk about that a little bit, that would help me.
Yes, sure. Let's look at maybe a problem. So the problem that I gave you had to do with 5 over 512, is that right? For the homework, is that right? Say that again? Okay, that sounds good. And then another problem having to do with okay, I just didn't want to do the problem that I had assigned you.
Oh, why not? We'd let you.
Exactly. So give me 1 second. And I'd like to do a problem.
Something like 5 or 3.
Okay. Let me come closer to you just to look at the 5 and 3. Yeah, and I'm just going to make one of them in just a second.
So I kind of figured it out because I drew the picture.
Yeah, the picture's what's supposed to go.
But some of the other ones were a little bit tricky.
I think the trickier ones were the ones in the notes that were, how did you?
Yes, fine. So here.
Oh, the bigger areas, like this square and that square and that, like that. Is that what you're talking about?
Oh, maybe you're talking about the CDF as well. But let me just do an example.
Okay. So then we'll see if this is what we need. Are you recording?
Yes.
Okay.
Yes.
Sure.
So thank you. So as an example, let's say f of x comma y is equal to, I'm going to write down the symbol k. K times 2x plus y, that's what I'm going to write. If, let's say that 0 is less than x is less than 3y is less than 6. So that's what I, and 0 otherwise. And let me do a few parts to this made up problem. So part A, I'm going to say find k. I think I asked something in homework number 2 where I'm asking you to find K, but I think I gave you a, as opposed to what's written on the board being a probability density function. I'm asking a question here. I don't have homework 2 right in front of me.
Number 4.
I think that I gave you a probability mass function. Was that right?
Yeah.
Okay, so this is a little different, but it involved what Chris was asking about in terms of integration. And so here's, that's part A. Part B, let's say find f sub x of x, the probability density function of x from this. And and then maybe part C will say find the Cdf. And these problems will, at least the last one, will take a little while, okay? And I think that maybe your question will be answered by this. So for part A, Chris, the first thing that I think of is this. This PDF, so I didn't write up all the words, but this is the joint PDF for the random variables, big X and big Y. Okay? And so here, where is it defined to be non-zero? Well, the X values run from 0 to 6. The Y values run from 0. If I solve here, that 0 is less than 3Y, which is less than 6. That says that Y has to be between 0 and 2. So it's this rectangle for which we're, in some sense, integrating over. But there's also this other restriction that X has to be less than 3Y. So this, if I look at X equal to 3Y, that says that Y is equal to X over 3. So that's what I'm going to write down. And when I graph that, what you end up getting is this line. And this line that I've drawn, it splits this rectangle into 2 parts. And so I need to know where is the region for which f of x comma y is non-zero. Okay, so that's what I'm going to be integrating over. Okay, so here I will just pick a point. Let's say I pick this point. Let's say I pick 1, 1. Okay, that's in this top region. Does it satisfy this? So this is the point 1, 1. Okay, the x value is 1 and the y value is 1. 0, is it less than 1? Yes. Is that 1 less than 3 times 1? Yes. So that means the top triangle is what I'm using. Is that okay? And that's the way that we decide what's the region where the PDF is non-zero.
Could you just say x is less than or equal to 3y, solve that equation for y, we'd have y is greater than, and then know where shading above?
I would still test a point. That's what I would advise, because it's easy to get confused about above, below, depending upon what the curve looks like, okay? So it doesn't have to be a straight line. So that's what I would do, and that's my advice to you. Here, part A says find K. And so to find K, what I'm going to use is that I know that if you do the double integral from minus infinity to infinity and from minus infinity to infinity of the joint PDF, you need to get, what value do you get? It's a characteristic for the joint PDF. If you integrate them, what do you get? Say it again, Ruth. That's correct. Okay. Listen, I want to tell everybody, one of the things that I like about you guys is that you have a good ability to say, this is what I know and this is what I don't know, which allows me to help you say, okay, we're good here, we're not good here. So if you don't know something, you should say. We make sure that we give instruction of what it is. All right, so here, note we have this fact. The double integral from minus infinity to infinity, minus infinity to infinity, of f of x comma y, dx dy. That's what I'm writing. And it turns out that the limits of integration, you can do them either way for us. There are some problems for which, not in this class, there are some mathematical instances where you cannot, if you switch the order of integration, you don't get the same answer. So the order of integration can matter. But in this class, we're not going to be able to run into this because of because of characteristics of the joint PDF. We can't get into the situation that mathematically can happen where switching the order of integration does yield different answers. For us, it doesn't matter what order of integration we do. Okay, so I know this is equal to 1. Okay. Now, the question is, well, if you have spots where you're integrating and it's 0, what you're integrating is 0, your answer is 0. Is that okay with everybody? So, in some sense, you could say, look, this guy right here, let me take my time. This is one of the good things about meeting together, that we can look at it very carefully. And you could split this up into 2 intervals. You could say, well, let's go from minus infinity, this is the x, the y values, to 0, so minus infinity to 0 for y. That's all of these guys, okay? Everything below here. Is that all right? That's what I'm talking about. You know? I haven't written everything down yet.
Okay, I'll let you write it in the last.
Okay, and there should be an equal to. So I'm just looking at this guy. And then here, I'm going to let this be from minus infinity so for let me look here. So I'm going to write down minus infinity to infinity, but before I go any further, I'm going to look at that. So here, the y values are down here, and I'm letting the x values go whatever they want. Okay? Plus the integral from, I'm going to say 0 to 2 of the same thing. Plus, and now I'm going to have the integral from 2 to infinity of the same thing. Let me move the camera so I can take a look what's there. So really, I just broke up the xy plane, if you will, into regions for what we're integrating over. So I'm taking my time. What I'm thinking is the following. What I'm integrating over is here and below, this strip, this section. So I'm really taking the xy plane, and I'm splitting it up into 3 regions. Here, this whole thing underneath, this middle strip. Is that okay? And then what's above? Is that okay? Okay, but here's what's happening. Let me go back to the line where we are. Yeah, Chris, is that all right?
Show me again on the picture, please, Claire.
Yes, sir. The first integral here is this. All here. That's what we're talking about. Everything here. That's the first integral.
Okay.
So the y values run from minus infinity up to 0.
Okay.
And the x values run from minus infinity to infinity.
Okay.
Is that okay?
How does that relate to the original problem and why we're doing that?
Okay, the reason that we're doing this is because I'm going to integrate f of x comma y. And so f of x comma y a lot of times is 0.
Okay.
And
So
so
that first part is taking care of the 0.
it's not just that first part, but that first part is involved where the function we're trying to integrate is 0. That's right. So Chris, I'm going, and everybody in the room, I'm taking my time in this problem. I'm going to show you once I get to a certain point that I would have just written down, here it is, okay? But right now, this is what we have. Okay. So when I look at, over this bottom half of the plane, when I look at the f of x, if you wanted, you could split it, well, the f of x over this bottom half of the plane is going to be defined to be 0. So I'm just going to say that's 0. Plus, here's the integral from 0 to 2. And so we're talking about, take our time, we're going to draw everybody's attention. We're talking about this region right now that we're integrating over. A lot of the times in that region, the f of x comma y is 0, here and here. Where is it non-zero? It's here, just over this triangle. So it's over that triangle that I need to describe. So for the x values, so here's what I'm going to do. And Chris, I want to tell you and everybody in the room, I don't think this is necessarily easy or hard. It took me, when I was a student, some time to get it. Okay? So it wasn't like I got it immediately. You're integrating with respect to y hour. Okay? So what you do is you say, for a fixed y, I know I'm integrating y is running from 0 to 2, this band right here. For a fixed y, what do the x values run from?
3.
Okay, that's right. The x, wait, I didn't pay any attention to you. Say it again.
3, 1, right?
That's what they run to, okay? But what do they run from? What's the smallest?
0.
0. Okay, so then I go from 0 to 3y. And then what is f of x defined to be over that region?
K plus 2.
And then this will be dx dy. Okay. And the rest of the spots from minus infinity to infinity of f of x comma y, the rest of it, in between 0 and 3y, the f of x comma y would be equal to 0. So there's no use putting it down, if you will, because when you integrate it, you're just going to get 0. Chris, is that okay what I said? This part is 0, Chris, because if I go beyond here, above here, I should say, then f of x.
Oh yeah, I got it. I got it.
Okay. And so what I think, Bob, is tough is that to realize when you integrate dx dy, you're saying, well, y's going to move, but for a fix, just for a second, fix it. Let's see how the x moves, because it's the inner integral. Okay? Is that okay? So we kind of read from left to right. We say, oh, look, the y's are moving. Well, fix a y. What do the x values do for that fixed y? Okay, so that's our problem. So this ends up being, if you will, an integral from 0 to 2, integral from 0 to 3y of k, 2x plus y, dx dy. So now it's just a matter of integration. Symbolically, that's all we look at. I think, Chris, I'll go ahead and finish this part, but I think that I've gotten to the spot where your question lies. Are you satisfied with what we said?
Yes, with this one. But after we do this one, I have another one. But yes, like this one I understand a lot better.
Okay, good. And so let's go ahead and do some of that. Finish this one, I mean. So here, this is equal to integral from 0 to 2. I'm integrating with respect to x. So this will be k times 2x squared over 2 plus y times x. And then I want to evaluate this as x runs from 0 to 3y. So this is x factor. And then after I get an answer, I integrate with respect to y. Move the camera and then wrote it written here. So let's see what's here. That's what we got. I'll make a little space there. Actually, which okay. All right, now stop it. Okay. Fuzzy. Now it's fuzzy for me. So we stick in, first of all, x equal to 3y. We get an integral from 0 to 2, k. And here, we stick in x equal to 3y, so the 2's will cancel, the 2 over 2. And we're going to have 3y to be squared. That's 9y squared. And then, remember for x, we're sticking in 3y. And so that second term is y times x. So it's going to be y times 3y. So that's, I think, a plus 3y squared. And then when you let x be 0, you're just going to get 0. I mean, you're looking over there. 0 squared is 0 plus 0 times y. That's 0. Is that okay with it? That's what we have. And then we integrate with respect to y. Okay, that's equal to, here we're integrating with respect to y. Well, before I do the integration, I can simplify this a little bit. So here it's 12y squared dy. Okay. Well, this is equal to, so it would be 12k y cubed over 3 is an antiderivative from 0 to 2. I let y be equal to 2. When I do, I'm going to get 12 times k times 8 all over 3 minus 0 when I let x be 0. That's what I get. So this is 32k. That's what we end up getting. Now, that was this integral, okay? And Chris, one thing I want to tell you was I kind of went very carefully on this right-hand board to try to break up this double integral into the parts. But really, I would have gone directly to here. Okay? So once we get comfortable enough, that would have been the first thing I would have written down and said, this is the thing that has to be equal to 1. Because that's where the f of x comma y is non-zero. Okay? So that's what I would do. But it takes a little time to get experience to get accustomed to that. Anyway, here's where we are. And so what stands out to me about this is that we get a conclusion that 32k must be equal to 1, so k must have been equal to 1 over 32. Is that okay? Any questions about what I did? So remember that double integral has got to be equal to 1 of the PDF, the joint PDF. And so this is what the double integral was equal to. I said equal to 1. Let's be solved. And your problem that I gave you for homework is not going to be a double integral. It's going to be a double summation. But it still needs to be equal to 1. Yeah. So it's okay. The second part that I said fine was f of x of x. And what do we mean by that? What do we mean by f of x of x? This was part B. What that is it's defined. It has a specific definition. Its definition is the integral from minus infinity to infinity of f of x comma y dy. So when you're finding the probability density function from the joint, okay, you integrate with respect to the other variable. Okay, that's what you do. So in our picture, what I would notice is that the x values run from that's what the x values run from, 0 to 6. And in this case, we'd say, well, I want to integrate this f of x comma y over this region. Okay, that's what I'm going to do. So here, I fixed the x values run from, I'm looking right here, the x values run from 0 to 6. These are the x values, they're running from 0 to 6. Fix one of them. Okay? You fix one of them. What do the y values run from for that particular x value? So when I say x equals to this number, that's a vertical line. Okay, x equal to that number, vertical line. Where does it intersect this region where f of x comma y is non-zero? Well, it's over this portion of this line. What do the y values run from for that portion? That's what they run from. The biggest value is 2. I'm just talking about for this particular point, this particular x value. The biggest value is 2. The smallest value is right here. But if I had picked another x value, it would have been from here to there. The y value is still 2 every time. So the top y value is 2. So I'm going to write down 2. I'm going to integrate where this guy's non-zero. This is 2. This guy is coming from x equal to 3y. And if I solve for y, that is x over 3. And here I would have 1 over 32. That's what we found k to be. 2x plus y. This will be dy. And we'll finish it up over here to the right.
Question.
Yes, sir.
One of the other questions with the integrals there. So x over 3. Why have we changed it to x over 3 because we're integrating with respect to y? Is that correct?
That is correct. So here, you want to know what do the y's run from. Okay? And so here, I hope it's clear that on this particular vertical line, the biggest y value is 2. Here is the smallest y value. Is that okay?
I get that part. I guess I understand now because we're doing the f of x of fx of x.
Right.
So we're integrating with respect to y, and so
That's
that's why our integral has to be x over 3 instead of 3y.
It has, yes, but I would give it a little bit more details. Why is it x over 3? We're describing y values. So when I look at this line, y, if you will, x equals to 3y, right? When I look at this line, I want to solve for y. I want to know what y runs from. Does that make sense? So I solve for y. It's okay what I said, please?
Yes.
Okay. So that's where we are. Okay, so going ahead and solving this, remember I'm integrating with respect to y, so I have 1 over 32, an antiderivative with respect to y. This is, the 2x is a constant, so I write down 2xy, and then plus the integral, the antiderivative of y is y squared over 2, and I need to evaluate this as y runs from x over 3 to y being equal to 2. So, you know, in the previous example I did, we just had zeros as our bottom integral limit of integration. And so when I stuck in 0, I get 0, okay? But here when I need to be careful to stick in the bottom integral. So this is 1 over 32, 2, now for y I'm letting that be 2. So this will be 4x plus, here this will be 4 over 2, so I'll just write down 2. And then I have to subtract from that what I would get when I let y be equal to x over 3. So that would be 2 times x over 3. So it's 2x squared over 3. And here, when I let x be equal to y be equal to x over 3, I'm going to get x squared over 9, so, and then I have to multiply that by 2 in the bottom. So that's what I get. And so here's a kind of a simplified version of the answer. So let's see. Here I've got, this is going to be, well, there's a 4x, there's a plus 2, and there's a minus. This will be 12 over 18 minus, so it'll be 11x squared over 18. And that's a way of leaving your answer. So that's the function you would integrate to find out about x, the probability of x. Yes, sir?
Dumb question, but inside the second parentheses, why we switch that from a positive to a negative, where it says 2x squared over 2?
Because I made a mistake. I didn't mean to. It should be plus, so I made a mistake. So this is 12, this is going to be 13. So thank you, Bob. It wasn't a bad question, I made a mistake. I wouldn't pay enough attention. Is that okay with everybody? Okay. All right. The last part was the CDF, and that's not so easy. Okay? But I asked you to do, I think, a CDF on the homework. Is that right? So might as well look at it. Okay. You're okay with what's been said so far? Okay. Yeah, I when I was doing it, I knew, I suspect, I didn't know, that this would be the part that people would have question on in terms of characterizing what the region of integration, the limits of integration. When I was, there's 1 or 2 sections in a Cal 3 class for where this would be done only. So we're talking about, you know, less than a week where this is mentioned in the Cal 3 class that you might have had some time ago. Okay? And so it's easy to say, well, I didn't know that was going to be important for us. But it is for this class. Okay, the CDF. I want to redraw my picture here. I'll probably redraw it several times. I did see that. There we go. Come on. This is the region we're in. For the CDF, so F is part C. F of AB. Okay? This is equal to the probability that X is less than or equal to A and Y is less than or equal to B. Okay. And so this is going to be equal to the integral from minus infinity to B minus infinity to A of F of X comma Y dx dy by the definition of this probability, characteristic that the joint probability density function has, the guy that you integrate to get the probability that X and Y are in those regions.
Can you explain, in the notes I still had some problems with, when you go from f of AB to that probability of X is less than A, Y is less than B, can you explain what that second part means again?
So you're talking about go from here to here?
Yes.
Okay. So it is the definition of what the CDF is. So here, let me just write down. This is from this equality right here. It's from the definition of the joint CDF. Okay. So what is a CDF? If I say just sub X, okay, so we'll make it a little bit F sub X of something, A. And we got this random variable X. Somebody said, what is that? That's equal to, it's defined to be the probability that X is less than or equal to A. Okay? That's what it's defined to be, okay? So here we're talking about a joint situation where we're saying, what's the chance that X is less than or equal to A and Y is less than or equal to B? That's what we're saying. And so that's just the definition. That's what it means. That's what those symbols are trying to indicate.
Are the A and the B those are those limits of integration? Is that what we're talking about?
That is correct. And what they are, so here on my picture, Chris, I can talk a little bit more about it. I mean, if A were minus 1, here's minus 1. And let's say B was minus 2. Okay, so you're talking about this has to happen. You have to be less than minus 1, and you have to be less than minus 2. It's this region that we would be talking about. Okay? Is that okay with everybody?
So I'm going to draw that picture, so say that one more time, I'm sorry.
Yes. So if A were equal to minus 1 and B was equal to minus 2, the A represents an X value. You can see it here. Is that okay? And then B represents a Y value. And so I'm just saying, well, what if B were minus 2, just to give a concrete example, and A was minus 1. Well, here's where the X value is minus 1, here's where the B value. If you want to know what's the region, so I drew those lines. X, I'm sorry. You know what? X is minus 1.
I'm saying, is that?
Yeah, I messed this up. So B is equal to minus 1, and A is equal to minus 2. I'm sorry. X is minus 2. Okay, so I messed that up. So let's say that a little bit. Right. So where is A equal to minus 2 right here? You think of that as an X value. You draw a vertical line. B is minus 1. You think of a horizontal line. Y equal to a number that's a horizontal line. You want both of these to happen. So this, just think of this cross here. It splits the XY plane into 4 regions. 1, 2, 3, 4. Is that okay? Mm-hmm. What are we talking about? We're talking about, we want the region where the X values are less than or equal to minus A. That would be here, back. So it's all of this region here. But we also want the B to be less than minus 1. The B less the minus 1 is below here. So when you say, I want this region intersected with this region, what do they have in common? It's this. Is that okay? Well, look, we have this interval. So that's what the definition is, integral here. And if you integrate this PDF over this region, what is the PDF over this region? What's the PDF over this region? 0. And when you integrate 0, what do you get? 0. Is that okay? So I'm going to stop for a second. Look, this PDF, what we can think of it is, if you think of this table as the XY plane, I'm putting XY axis. The PDF is some function that's going to be above it. And when you do the double integral, what you're finding, let me back up for a second. If you think of the XY plane, and you talk about a function, f of x for r f of x being PDF, is going to be a positive quantity, okay, non-negative. Okay? So it's going to be above the x-axis. I'm talking about XY plane, okay? One variable, f of x, PDF. When you integrate that f of x, what are you finding? Go ahead and say it, Shannon. There. When you're having a f of x comma y, what are you finding when you integrate it? Double integral. It's not an area, it's a volume. Is that okay? That's what's happening. Is that all right? So, here, we're looking at integrating over this part some function. What the function is, it's always 0. So, in the xy plane, here, I don't know, let's see, there's the xy plane. I'm making right there on this table. We're talking about over here. And on this region, the function we're trying to integrate is the same as the table. Is that okay? It's 0. And so its integral is 0. Is that okay with everybody? Okay, so here what we can say, if A is less than 0 and B, or B is less than 0, then f of AB, so when you're in this type of situation, is going to be equal to 0. Is that okay with everybody?
That would be like our case 1 then.
Yes. I didn't know, Jackie, that must have been what you were saying. I couldn't hear.
Yeah, I told myself, but we left our or off.
Yeah, it's an or. If either one of those happens.
We put a comma, so it's like, oh, I'm a mistake.
Well, you could still break it up into other parts, but what I mean here is that, you know, if the B value is less than this, then you're down here. You know, no matter what A is, you're down in here, and definitely what you're integrating is 0. This part. Okay, okay, what I'm going to do then from now on is really work with A being the A. I'm going to look at A primarily. It's going to be, so really this is, A is less than 0, you're going to get 0. Well, the next kind of grouping to consider, maybe to consider A by, is A represents an X value. Well, what if A is in between 0 and 6? Then you know, you're going to get some of this region here involved. Does that make sense? Well, it depends on what B is. Okay? So here, I'll go back and forth a little bit. I'm sorry if I'm taking too long on this. I'm boring. But here, if A is between 0 and 2, something like that. So this is kind of, as Jackie said, like case 1. And this is like case 2. Okay. Now, if I go back to this picture of where the joint PDF is non-zero, I say, look, what we're looking at is this. Something like that. That's my A right here. That's mine. Well then, B, if it's less than 0, we've already handled it right here. We know the answer is 0. So the question is what if B is in between 0 and 2, maybe? Worry about that. But if it's in between 0 and 2, we get something like this. Does that make sense? And the question can be, well, wait a minute. Let us handle the part where B is in here first, okay? So this would be, so the B value, so this is going to be subcase 1. Okay, so I need a little bit of time to think about this. So the b value is going to be such that 3b is bigger than 0, but yet less than a. Okay? That's what I'm going to look at.
The 3 comes from prior when we had 3x.
Here.
Or
Is that okay with everybody? This says that b is less than a over 3. Is that all right? Write it that way. Okay, so that gives us this region. And so what I would have is this part right here. So, and I'm not going to do very much more of this. Just a little bit more. So what we do is we integrate. And so I have the double integral. And this time, what I'm going to do is I'm going to do the double integral with respect to x last, and then y. Okay, so here I'm going to have the y's, the x's go from 0 to a. Where do the y's go from? Well, let's see. The y values for a fixed x, okay, they're going to go from this line to this line. So that means that the y values are going to go from 0 to, I think, here this would be the b values run from a over 3. I want to look at something. I want to make sure that I didn't make a mistake. Okay, you give me 1 second. It's going to be more than a second. I want to make sure that I didn't make a mistake. Okay, I think it's better, because this doesn't look beautiful. I think it should have been just B here. I think what we should do here, this should have been, I think, B, to what B is, whatever B is. I think that's what it should be. Okay, so this was B. I think it's better to leave it. I want to change it. So, okay, so that's what we have. I want to change it back to dy dx. Let's look at it this way. So the a value, here these run from, let's talk about the y values. The y values run from 0 to b. Okay. You know, I didn't draw this very well. So here, the b value is less than 3a, so it's going to be somewhere down here. Okay, that's what it is. So the b value, something like that. The b values run from, the y values run from 0 to b. For a fixed one, the x values run from 0 to this line for the x, so that would be 3b.
quick question.
Yes.
Why do the y values run from 0 to b?
Well, because it says y is less than or equal to b.
Because that's what we're looking at
Because
here.
that's the specific subcase we're looking at. Gotcha.
That's this part, okay?
I was looking at the whole picture and I was thinking it was the 3b that was starting at, but we're not starting at 3b. And how do you choose the order of integration? That was another question I have. How do you know whether to do dy or dx first?
Okay, so here I'd like to go over this. This is be the part that we'll conclude with. But really, Chris, what determines it for us in this case is that I said, well, let's look at b's that are in this situation. So I'm going to go back and forth between this picture. If your b value is something less than a third, less than a over 3, then we're talking about this region that we're integrating over, okay? And it doesn't matter if we do dx or dy. But what I said was, well, let's see. Here we run from now I'm trying to describe this, okay? That's my b, okay? How am I describing this region? So what do the y values run from? They run from 0 to b, or a particular 0 to b value. What do the x values run from? Okay, the x values would run from this line to here. And really, I shouldn't have put b. I should have put, I should have put y, 3y, not b. And then we would have had this. It's 1 over 32, 2x plus y. I'm sorry it took so long to get this down, because it's not easy to get. But that's what it would be. And again, what I'm doing is, okay, look, what if we have a b that's less than the a over 3, this line. Okay? If it's bigger than a over 3, Chris, here's the problem. So let's say it's here, okay? And I'm talking about integrating this. Then for that, I would have, well, what if the y values are in here, and what if the y values are in here? Does that make sense? Okay? So that's why we break it up into this situation.
I guess the only other thing that I'm still stuck on is I still don't understand the order of the integration. That's where I'm still stuck on. I'm getting the limits now, but why do we choose dx, dy instead of dy dx?
Okay.
Because we could choose, instead of putting 3y there, from 0 to 3y, we could put from 0 to whatever x, and then we would integrate with respect to dy dx instead of dx dy.
So let's take a look at, so if we were trying to do the other order of integration here. So let's look at what we're doing, dy dx. Okay, that's what I tried to do just for a second. Okay, so it's not easy. Let's see. Here, if I look at something that's in this is my b. Okay? My b is for any b that's down here. Okay, if I wanted to integrate that, what I would do is I would say, okay, the problem is here. I don't want to go all the way up to here, so it affects the A choice. Okay, so if the b is down here, then I have trouble about this part I don't want to be including in this subcase. So I've got to re-describe this. That's the problem. Is that okay?
We're talking about that little teeny triangle.
Yes.
And so if our b, wherever our b is at, we have to, our a would hit somewhere in that little teeny triangle.
Yes, and so that would affect what our choice of A was. So if A's out here, I'm going to throw this part away.
Right.
Does that make sense?
Yes.
Okay. And so here, let's see what we do. So I'm doing dx is last. Okay. And so you'd say, well, what would the dx go from? Well, we normally think it's, into a, but it's not. Okay? It stops here. So for an a, we'd have to stop it here. That's the problem, because we'd like for it to go to a, but that's why I don't want to do this type of integration in this respect. So I have to stop it. So what would I stop it at? I would stop it at, well, it's hard to describe because it's going to be in terms of b. Is that okay? So here, I still have, this will go from 0 to b, and this particular guy, what would it go from? It would go from for this particular b value, this a would have to be so it's got to be 3b, I think. That's what it'd have to go to. Is that okay, Chris?
So it's not going all the way to
The A
line.
Yeah. No, it's going to this line, but it's not going to this line.
So could it go from 0 to 3y?
What is it?
Instead of 0 to b, in my head, for some reason, I'm thinking it's going from 0 to 3y. Why is it going from 0 to 3b?
So here, this is for, okay, so,
Because we're integrating with respect to y first.
yeah, we're integrating with respect to y first. So what do the x values go from? So we're thinking, oh, the x value goes from 0 to a. Okay? That's from here to there. Is that okay? For describing this the way we have it described in this region. But over this region, what we'd be integrating is 0. So I don't want that part. Does that make sense? And so that's why I have to re-describe it. Is that okay? All right. Anyway, these are kind of longer problems. The problem that I gave you to do, if you mimic what the problem was done, I think it'll be okay. I've given you something too.
And I was working on that one last night, and that's why I came across all those. I was mimicking it, but then I was like,
Why are we doing this?
yes, exactly.
I hope this makes some sense.
It does now.
All right. I want to open up the floor to anything else. I'm going to stop there because there's lots of cases in the problem table.
Yeah, I'm okay with those. I'm okay with all the cases. That was where my
I'm
issue
glad.
was at.
Would anybody else like to ask something from the homework?
We haven't even started between 7.
Did you vote? Because I looked at it.
Which one were 2 and 7?
That's the, well, I guess we'd look at 2 a little bit, the one I called you about yesterday.
I don't want to look at it.
Okay.
That's what I want to do. Because there's something, I'm glad. So,
Yeah, we just ran out of time, so we.
yeah,
we're like, we'll go with
before I get to it, let me write this down here on the side. I just want to keep this here.
I remember them this week.
All right, So I wanted to look at those other problems. Thank you for being patient. First of all, I have done 15 videos, and in the last video, I took a little time to talk about something that I hadn't talked about before. And so, Shannon, it was problem 7, was the last, is that the last problem?
Yes.
Okay, so here, for problem 7, what does it say?
It says prove E parentheses the sum of I runs from 1 to n of Ci xi. E parentheses sum I from 1 to n Ci xi. C sub I, S sub I equals sum from 1 to n of C sub I times E parentheses X sub I.
Yes. Okay. The first thing that I want to tell people about for this problem is that I mean for this problem to be done a certain way. And so what kind of proving technique do you think should be involved with this?
Induction.
That's right. And that's what I mean for it to be done. Okay? But I want to tell everybody that I haven't defined kind of how we talk about this expected value. I'm hopeful that you will do it by induction, okay? But in general, we have defined, and I did this in lecture 15 with Shannon. When you asked me how far did you have to go to do the homework, I said 12. Okay, but so you can do this problem with induction, okay? But if you think, what is this expected value defined to be? I mean, so we have defined the expected value of g of x, xy, when we have a joint. And when we have two random variables, it's going to be the double integral. Well, if g x, well, it's either going to be the double sum, okay, x, y, gxy, f of x comma y, or it's the double integral, here, write down gxy, dx dy. I forgot something. What did I forget? Yeah, sure did. Okay, that's what their definition is. But this is when we have two random variables. How many do we have here? Mm-mm. You could think of the sum as being 1, but if you think of them as individually, how many do you have? N. Is that okay? So the problem is something like this, is the expected value of C1x1 plus C2x2 plus C3x3 plus CNxn, okay? And the question is, how would you do that? This will be a function, g, not on two random variables, but on, okay, I'm going to say it again. This, g, is a function of how many? Well, I've got written 2. This is a g, a function, but not on two random variables, rather on n. And I hadn't said how to do it. And so it was on 15, I said, oh, look, wait a minute, this is how you would do it. But I'm not expecting you to be thinking of it this way. What I'm expecting is that you would do it by induction. Okay, that's what I'm thinking. Does that make sense? Is that okay what I said there? And so you would do it for one is nothing. Okay, it's the same thing. If you need to do it for 2, we kind of did that. But for 2, you would use this. Okay, in either case, we kind of did it. And then you would extend it. Does that make sense? What if you had n and you would use the induction hypothesis to give it to you? It's okay? That's what I'm thinking. That's problem 7. And really, once we had problem 7, we could do that, use that result for maybe other problems. And problem 2, we might use it. in doing the problem 2, so I'm going to move over here because I want to say something about it. So. Yeah, I'm glad I wrote this over here and embraced it. Good, John. Good. That's good. Yeah.
Chris has a picture of it if you need it.
Okay. Well, I know where it is in the lectures. It's at 53 minutes. I know it is. So I can look at something. Okay, so I would, the problem for problem number 2 is to find a formula for covariance of the sum as I runs from maybe 1 to n of xi. Is that right, comma? The sum is j runs from 1 to m of y j. Okay? And so in doing this, here's what I would like for people to think about. I'll lead you just a little bit, and I'm sure that I will get some right answers here. Okay. What is the formula for covariance? Not its definition, formula.
Expected value of x times y minus the expected value of x times the expected value of y.
Okay, so here's what Chris gave me. Accurate. That's right.
Just about.
Okay. Is that okay? That's the formula that we have. All right. So here, this would be equal to the expected value of what's playing the role of x? Oh, for that formula over there.
The sum of 1 to n of xi's.
That's exactly right. Times
The sum of j from 1 to n of yj.
that's right. Minus, and here this will be the expected value of the sum of the xi's minus, not minus, but times the expected value of the sum of the y's. Okay? And that's just put there. I ran from 1 to n, I run j running from, just j running from 1 to n. Okay? These guys we can handle by part problem 2. Is that okay? Because here, instead of having, your CIs in the part we're looking at, the CI every time is, what's CI understood to be here? 1. Same thing for here, is that okay? And so you could say this is really is going to be the sum of the expected values. Okay? What I'd like to recommend, and Shannon, this is what I was trying to say on the phone, is I want to talk about this guy for a second, just this guy. But I'm going to talk about it in terms of it being analogous to something I do in Lecture 15, okay? So in Lecture 15, I have to find this.
So real quick, you're saying those last two values are 1?
I'm saying C sub 1, analogous to what's written over here, is 1. Chris, look at where my finger is. What I just want to underline. Look at this part right here. Okay? Xi, sum. What's missing is the C sub i's, but we could understand the C sub i's to be equal to 1. And so you can just use that formula. That the answer is going to be the expected value of the, the answer is going to be the sum of the expected values. Is that okay? So, well, I'll write this above, and this is what I was getting Shannon on the phone. I said, Shannon, this would be expected value of x sub 1 plus expected value of x sub 2. I'm going to stop. Okay, plus expected value of x sub n. That's the first guy. And then what do you multiply that by? what I was thinking was that we would expand this, okay? And we'd actually do these multiplications, okay? And see what you have there. Is that all right with everybody? But I'm going to work on this part. I'm going to do something analogous. Okay, analysis part. Okay. In lecture 15, what I look at is something of this sort. So we have the variance of x of 1 plus x of 2 plus x of n over n. It says, look at that. Tell me what that is. Okay? So in the variance, I'm looking at that. Okay? So this is not the problem we're working on. Okay? I'm doing something analogous. Is that all right? So I'm saying, hey, find this. Okay? Okay. With some conditions, okay? But I say, look at this, okay? So here, what is this? This is defined to be the expected value of this guy to b squared. Remember the variance formula? It's the expected value of the random variable b squared minus the expected value of the random variable and all of that to be squared. Is that okay with everybody? Okay, now what I want to do is I want to look at just that expected value of that sum over n to b squared. That's the only part I want to look at, because this is what's going to be analogous to this. The expected value. So I'm just looking at one part, okay? I just say, look at this. Okay, so look at this, okay? All right, so Shannon, everybody else, I could have written this guy down in sigma notation or something. I chose not. Let's write it out. So that's what I was saying in the phone. Let's write it out. So what would this be equal to the expected value of? Well, it would be x1 plus x2 plus xn over n times x1 plus x2 plus xn over n. Because that's what it means to square something, multiply it by itself. Is that okay? Okay, then let's multiply it out. So the bottom's easy. I like doing what's easy. The bottom is n squared. And the n squared, or 1 over n squared, is a constant. So in terms of the expected value, you can pull it out. Is that okay with everybody? So it's 1 over n squared times the expected value of this guy. Okay. Now I've gotten to the point, it took me forever, it seems like, but I've finally gotten to the point where we can do the work that's analogous to what we need to do. At least, I'm going to do more than what's needed, I think. Okay. So this is going to be the expected value it's got 1 over n squared out front of it. This is the expected value. Let's multiply that together. What would I have? I'd have x1 times x1. How am I going to do this multiplication? I'm going to take x1 times everything over here. So then it'd be plus x1 times x2 plus, and eventually I'm going to have x1 times xn. I'm done with the x1 in the left. And then I'm going to have plus x2 times x1 plus x2 times x2 plus all the way up to x2 times xn plus, and I'm going to keep going. And I'm going to keep going, and eventually I'm going to get to plus xn times x1, and then I'm going to add to that all the way up to xn times xn. Is that okay? Okay. And so, Shannon, I think that that's going to be something that's going to help people doing that problem. That if you write down, so we had the variance of two sums, you write down the sum, x1 through xn, maybe times the sum of the y's, y1 through ym, multiply them out like this. And then you're going to have, if you will, you could rewrite this, and this 1 over n squared, this particular is the expected value of, well, what I'd say is that it's xi squared, and you're going to have the sum of those. Okay? What do I mean? This is x1 squared, right? Later I'm going to have x2 squared. And then I'm going to have x3 squared. Is that okay? That's some of them. And then we got a bunch of other guys that are mixed matched. Okay? So here it's going to be the expected value of xi, xj. I and j are different. And I'm not saying how many we have of them. Okay? Just that we're going to have some of those. Is that okay? And so I think that that's a good way of progressing. Does that make sense, Shannon? So that's what I want to say. Is that okay with everybody? Does anybody else have a question for me? Anything from the homework, anything from the lectures?
Could you do a brief summary, recap, combination, comparison of PDF, CDF, all of those? Just so I can see a summary and a comparison of them. So it'll help me understand them better, I think, if I see comparisons. Does that make sense?
Yes. Okay. So, first of all, we got two types of render. The discrete. Okay? The f sub x of x. The PMF. What does it do? It's defined by f sub x of x equals to the probability that x equals to rho x. So that's the definition. Okay. 2 for continuous. F of sub x of x. And again, that's the PDF. Okay. It doesn't have that it's equal to the probability that big X is equal to little x in the continuous case. Okay. As a matter of fact, the chance of that happening is 0. Okay. What it is, it has one characteristic. Its characteristic is the probability that x is an element of some set. It is equal to the integral over that set of f sub x of x dx. So, let me go back a second.
So density is for continuous because we're doing integration, whereas mass is discrete because we're doing.
We're going to be doing, it just tells us what it is, but we'd be summing it to get certain things. Okay. So here for the second thing, maybe we talk about the CDF. So 1 for discrete. you have f sub x sub a, this is the CDF. It's defined to be equal to, well, in both cases, it's defined to be equal to the probability that x is less than or equal to a. And that's going to be equal to a sum over all x values that are less than or equal to a, that's output values, of f sub x. Okay, so I write it.
Can you slide the camera over just a little bit?
Yes, sir. Thank you.
Thank you.
And here's for continuous. Yes, x is less than or equal to a. For continuous. F sub x sub a, again with CDF. It's still got the same probability. But that's equal to an interval from minus infinity to a of f sub x dx. I'm going to say a few more comments. Those are symbols. So what I'd like to do is look over here in terms of the continuous case for a second. I'm sorry, the discrete case. So these two number ones. Look, the PMF just gives you, it's a function whose output values are the chance that big X is equal to that. So as an example here, if I said a die is rolled, I guess it's not, an urn has 3 red balls, 4 white, and 5 blue. Okay, that's what I'm looking at. Let's say X, it grabs red and sends it to 1, X grabs white, sends it to 2, and X grabs blue and sends it to 3. Okay. So I'm right here. Can you see it where I'm writing? Is it okay? Guys can hear. Then if I said, what is f of 1? What's f of 1 defined to be? It's the chance that X was equal to 1. When did X become 1? When you got what kind of ball? Red. Well, what's the chance you got a red ball? It's going to be 3 out of 12. Is that okay? So what's f of 2? Well, that means you got a white ball. Well, what's the chance we got a white ball? It's 4 out of 12. Is that okay? And what's f of 3? Well, that's the chance you got a blue ball, and that's equal to 5 out of 12. Is that okay with everybody? And so, sticking with that, if you were to ask the CDF part, if you were to ask the CDF part, I'm not going nowhere. Let's say f of 2.5. So let's stop. What does that mean? That is asking you, what's the probability that x is less than or equal to 2.5? Well, look at the output values for x. What were they? Okay, 1, 2, and 3. Okay, that's it. Okay. So here, the chance that x was less than or equal to 1.25, really the probability that x was equal to 1 or x was equal to 2. That's the only outcomes that we have. Okay. These are events. Can x equal to 1 and x equal to 2 at the same time? No, so it's just one of those answers. I mean, it's got to be just one at a time for those answers. So that means they're mutually exclusive events. The word or, in terms of set theory, corresponds to a what kind of set operation? Well, union, and which translates, if they're mutually exclusive, into a summation of the probabilities. That's right. So this would be the probability that x is equal to 1 plus the probability that x is equal to 2. What's the probability x is equal to 1? Well, that's nothing more than f of 1. Plus, here's f of 2. Is that okay? So this, if you want, is really the sum over the x values, the little x values, output values, that are less than or a less than or equal to 2.5 of f sub x of x. Is that okay? Look, it's this two sums. It's these two guys added together. Because what are our possible output values? 1, 2, and 3. But I didn't sum in 3 because 3 is not less than 2.5. Is that okay? Is that all right? Now, for continuous, let me do an example that's, I believe, good, John, is to get our hands on, okay? If we can understand very, I think. So let's say a person will arrive at a bus stop.
This is the continuous CDF, right?
You look at continuous random variable and do its PDF and CDF, okay? At least part of it. Between, or at random, and this is the example I've been doing, between 5 and 5:30. Let x be the time after 5. Let's say she shows up. She arrives. It turns out that this is a uniform random variable, continuous random variable. I'll write down continuous random variable. With PDF equaling f of f sub x, little x, equaling to, I was writing f sub x. It's really equal to, it's going to be 1 over 30 if x is an element from 0 to 30. Okay, and it is 0 otherwise. The reason we define it that way is because it would match what we need to have happen, what we'd understand to have happen, for the probability that x is in certain sets. So for instance, if someone said, find, so Jackie, somebody said, find the probability the person shows up, she arrives between, let's say, 5:12 and 5:15. That's our problem.
Would you include 12 and 15 since you said between?
It doesn't matter whether we include them or not. For an individual value for a continuous random variable, you get 0. So them being added on or not doesn't make a difference.
Okay.
Well, look, How long of a span is that? 3 minutes. I'm not asking anything hard, it's 3 minutes. And we're expecting her to arrive sometime between this 30-minute span. And we're thinking all times are equally likely. So if all times are equally likely, okay, she arrives at random, you know, in some sense they're all equally likely. Okay, what's the chance she arrives in this 3-minute period? 3 out of 30, 1/10. Does that make sense? That's what our answer should be. Now, how will we get it? Well, what we will get will be the integral from 12 to 15 of 1 over 30 dx. Okay? So that is the A that I had written down over here, Chris and everybody else in the room, would be from 12 to, the integral, from 12 to 15. Is that okay? Because x would have to be between 12 and 15 minutes after 5 o'clock. Is that okay? That's my A. And we integrate the PDF. That's what it is. So this is 1 over 30, x, evaluated from 12 to 15. This ends up being 15 over 30 minus 12 over 30, which is 3 over 30, which is 1/10. And that's what we expect. Is that okay? So that's what it does. Okay, now the CDF in general, okay, that's f of a, which is equal to the probability that x is less than or equal to a. And so here, let's start off with, remember what x is ranged from. Their output values are between 0 and 30. So let's concentrate on A for a second. What if A is less than 0? And they say, hey, what's the chance that they came before 5 o'clock? Well, we're saying there's no chance of that happening. They're going to arrive between 5 and 5:30. So this should be 0. Okay, but it corresponds to integrating from minus infinity to a of f of x comma, f of x, I should say, dx. Okay. But what is f of x for the region where a is less than 0? Well, we're thinking that our f of x looks like this. Okay, this is f of x I'm drawing. It's 0. Then in between 0 and 30, it's 1 over 30. And then after 30, it's 0. Is that okay? Okay, so here, if you're talking about a being less than 0, so a is here, you're talking about being over in here, what's the chance that this happens? You're integrating f of x, but what's f of x defined to be over here? 0. So this is equal to the integral from minus infinity to a of 0 dx, which will just be 0. Is that okay? It's the integral of 0. That's what it is. This part, the f of x is 0. You just get 0. If a is between, let's say, 30 and 0. And Chris, the reason I'm thinking between 0 and 30 here is because I know to the left of 0, we're integrating 0. But if I get something that's bigger than 0, let's say this is my a, then really I'm integrating from here back. So the answer for f of a, big F of a, is the probability that x is less than or equal to a, which is equal to an integral from minus infinity to a of f of x dx. But a lot of times f of x is equal to 0. So when does it stop being 0 to the far left? When x is 0 and above, does that make sense? So here, if you wanted, you could say, look, I could split this integral up into minus infinity to 0 of f of x dx plus the integral from 0 to a. So, you know, here I'm integrating, okay? Here's 0, here's a. So you integrate this part, and then you integrate this part to get the integral up to that part. Does that make sense?
Then the first one just drops out.
Well, yes, and why is it? Because what is f of x over this region?
0.
That's right. Okay? So we just end up getting from 0 to a of 1 over 30 dx, which is 1 over 30x evaluated from 0 to a, and that ends up being a over 30. It's okay? And then what if a is bigger than, and here I could have equal to, or here you can have equal to, 30.
Zero.
Okay, so here you'd still be integrating from 0 to a. So this is the probability x is less than or equal to a. It still is minus infinity to a of f of x dx. Okay, but here again we're thinking here is 0, here is 30, here's a. Okay. This is the f. Okay. So look, when I look at f of x, what we're integrating up to 0, it's defined to be something. Oops. After 0 to 30, it's defined to be something else. And then from 30 to a, it's defined to be something. What's it defined to be? F of x. 0. So that's the way that you can break it up. Is that okay with everybody? Is that all right? Okay, and so this part's going to be 0, this part's going to be 0. We're just integrating this. It's 130. X evaluated from 0 to 30. That ends up being 1. I didn't do the completion of the CDF in the discrete case. I just did one evaluation of it. F of 2.5, I think I did. But I hope that you get the idea from that. Here I did the full one. Would anybody, Chris, was that okay what I said? Would anybody else like, or would any other questions like to be asked? Because I got more for you. What was the answer? It's the sum as I run from 1 to n. Sum as they run from 1 to m. Covariance of xi, y.
Or yj.
So it's the expected value of the sum of xi times the sum of y, yj's. Minus this sum times expected value of this sum. Anyway, I'm writing this way so that you can't read it, so you don't get the idea. Which equals here. So first of all, this is equal to the expected value of x1 plus x2 plus xn times the y1 plus y2 plus ym minus, this will be the sum of the expected values by problem 7. So if you do problem 7 first,
Can we say based on problem 7 on this?
no, you have to put in these details.
Okay.
Okay. Which equals to, okay, so I'm going to leave both parts for a second and handle each one of them individually. So this is where we're at. So note, the expected value of, I'm going to handle them all at the same time. So this is equal to the expected value. I'm going to apply it out. I get x1 times x1 plus x1 times x2 plus, not x1, but rather y1. This is y2. And then x1 times ym plus x2 times y1 plus x2 times y2 plus xn times ym plus all the way up to xn times y1 and then plus all the way up to xn times ym. Minus. What this is the expected value of x1 plus all the way up to plus the expected value of xn times the expected value of y1 plus all the way up to adding up the expected value of ym. Okay. That's what we're looking at. I'll give everybody a second to look at it. This is going to be equal to the expected value of x1 y1 plus expected x1 y2 plus the expected value of x1 ym plus the expected value of x2 y1 plus all the way up to the expected value of x2 ym plus a bunch more plus the expected value of xn y1 plus the expected value of x all the way up to the expected value of xn ym. So I'm doing the expected value of this sum is equal to the sum of the expected values. Okay? And the way that you can think of this, even though we can think of this as the definition with the joint, we need a joint PDF every time between xi and xj. Yj, I should say. Or you could just say, I'm calling x1, y1 a random variable. I'm calling x1, y2 a random variable. And we think of the sum of those expected values is the sum of the expectations by a problem. So that's that part. Minus what? Well, now we think of multiplying these guys out. So how are we going to multiply these guys out? Well, these are n individual things times m individual things. Here we take expected value of x1 times everything on the right. And then we plus the expected value of x1 times the expected value of y2 plus expected value of x sub 1 times the expected value of y sub m. That's the x1 times, that's the expected value of x1 times each one of these guys over here. Now I'm going to do the expected value of x sub 2 times every one of those guys. So here I'll write down plus the expected value of x sub 2 times the expected value of y sub 1. Plus, you keep going all the way up to the expected value of x sub 2 times the expected value of y sub m. Gosh,
You're just so intense, you're just throwing chalk everywhere.
I hope not. I'm worried that I have high blood pressure or something. This is going to be the expected value. Now we work to the x of n's times the expected value of y1 plus the expected value of x of n times the expected value of y of n. And then we just thinking this way. We're just going to do a pairing off, okay? But before I do that, how many terms are up here? Well, wait a second. We said, oh my God. Well, with the x of 1's involved, how many of them are there? M. Okay? With the x of 2's involved, how many of them are there? M. So they're going to be M. How many M's are there? So how many overall are there? That's right. That's right. How about in here? Same thing. For each guy over here, you got one over here. Does that make sense? Well, pair them off this way. So expected value of x1, y1 minus this guy. Plus, what's the next one? I mean, we go on, we get all the way up to x1, ym minus, so we pair them off like this. Put them in places. Then it will be expected value of x1 times the expected value of ym. Plus, we did this for a long time. And then we end up with the expected value of x.
Should that be over y1
Yes.
to the left?
This should be y1 here. And here, this was x1, ym. That was x1, ym. Here. No. This should be y1 too. Okay? And then this is x1, ym. That's correct here. Okay? Plus, we keep going, and then we eventually get to xn, y1 minus the expected value of xn times the expected value of y1 plus, and it ends with the expected value of xn times ym, okay, minus the expected value of xn times the expected value of ym. What are each one of these? That's right. That's what it is. Okay? And so here, if you think about the first groupings going from the x of 1's, so you're fixing x of 1. And you just let it, and then the y's would run from j equaling 1 to m. It's exactly it. Is that okay? You can still look at it, but there it is. Is it okay? That's what I had kind of in mind. Let's do. It's okay? Okay. We are looking at where we are in video 15. And part of what I did today, I had to look at the variance of x1 plus x2 all over n. Take the variance of that guy. And what's involved here with the problem that we're having in this video, it's called the weak law of large numbers. And we had something called independent and identically distributed, okay? And identically distributed random variables are random variables whose density functions or mass functions are the same. They're the same. But they themselves, if you will, aren't the same function because they don't have the same input values. Not only do they have the same output values, they have the same chance of those being the output values. But it might not be the same, they're not the same function. Is that okay? And I gave an example, so I want to talk about this just for a second. Okay, so, I don't know, did I get this on the board? I hope that I did. If I didn't, there it is.
I'll do it really quickly.
Okay. So, so here's an example. Let's say a coin is flipped. This is the example that I gave. Define x sub 1 of heads to be equal to 1, and x sub 1 of tails to be equal to 2. And earn, or a ball, is selected at random. From an urn containing 3 red balls and 3 white balls. Define x of r, x of red, to be equal to 1, and x of white to be equal to 2. So x of 2, I should change this, x of 2. X of 1 and x of 2 are not the same functions. They don't work on the same domains. Does that make sense? They're talking about different things. But if I were to ask what the PDF is of x of 1, okay? So really we talk about its output value. What's f of 1? That's probably x is equal to 1. What is that? That means you got a what? A coin flip. Yes, what's the chance of that happening if we got a fair coin? And what's f? This is sub x of 1. What's f of x of 1 of 2? It's the only other output value you could have. It's 1/2. Is that okay? Is that all right? What is f sub x of 2 of 1? So how would x of 2 be equal to 1? That means you got a red ball. What's the chance you got a red ball? 1. And f sub x of 2 of 2 is equal to 1/2. They are not the same random variables, but their PMFs are the same. That's what it means to be identically distributed. Does that make sense? And when we talk about for identically distributed random variables, let's say I ask, well, what can you give me a relationship between the expected value of x of 1 and the expected value of x of 2? Can you give me a relationship between them? So how would you compute the expected value of x of 1? What would it be? I mean, how would you compute it? What would it be? It would be the sum over all the x of 1 values of expected value we're talking about. So if I just said the expected value of x, what would you tell me? Sum over the x's of what? You want me to help?
Yes.
X of 1 times f of x of 1. Okay. What would be the expected value of x sub 2?
The sum of x sub 2's of the x sub 2.
But x sub 1 and x sub 2 have the same output value. They both run from 1 to 2. And then that means that these guys are going to be the same. And f of them are the same, so their expected values are going to be the same. And the same thing for the variance. It's going to happen the same way. Is that okay with everybody? Because that's the way that they're distributed. They're probabilistically, they're the same random variable, except they just don't work on the same space, if you will. They're two different random variables, but the key characteristics of them are going to be the same. Is that okay with everybody? So it's like you're working with the same random variable. And a lot of times you are working with the same random variable. One of the things in these limit theorems that we're talking about in the chapter, at the end of chapter 2 of our text has to do with kind of looking at the average, comparing it to, and we have this weak law and strong law of large numbers. And what we're doing is, in some sense, we're saying, hey, if you do the experiment and you get a result, and you do it n times, and you say, well, what should be your average? You do something. How are you going to find the average? You say, well, let's do it a bunch of times, see what we get, and then divide it by the number of times we did it. That's what these guys are saying. Weak law and large law of strong numbers says this. Okay. It says if you do things a bunch of times and divide it by the number of times you did it, that ought to become what your average should be. And, you say, well, that makes sense. Well, that's right, but we're showing it here mathematically. But I'm going to tell you, if you just do something a few times and say, well, did you get the average? Not necessarily. I've seen basketball series where I say, that the best team won those 4 games. But, I'm sorry. I saw the team that won those 4 games, but if they played 100 times, it wouldn't have gone like that. Does that make sense? That team was red hot right now. Okay?
What do we say about the championship game?
No, I think San Antonio is the better team. But they are red hot right now, too.
I'm talking about Alabama.
If Alabama wins, I say that's average. But if they don't, then I say, well, they should play it that time. So when you take a snapshot of something, it may not be what normally occurs. But if the snapshot, if the picture that you look at is long term, you say, hey, this is what must be happening. At some point, okay, if it's long enough, you say, that team is better because they're winning more often. Does that make sense? So that's what these things have to do with mathematics. So that's what we're doing. All right, ladies and gentlemen, what I want to tell you is that 15 videos are up. I put up the 15th one at 9:45 today. You should be doing the standard pace on average 3.5 videos a week, so 14 videos at the end of the day. So I'm just barely ahead of where you should be. That's what you got to pay. We're not meeting again until I think June 20. We're June 27th? And that's when we're having a test, in 2 weeks then. Probably within the next 3 days, I will send out an email saying, here's what I would expect you to know. Part of it is going to be the proofs of these limit theorems. Okay? And I'm not through doing them, so there'll be 1 or 2 more videos put up probably by Tuesday. Okay? That will be part of the test. And then I'll probably on Wednesday, I'll send out, here's what you need to know for the test. And I will narrow it down, and some of it will be proving, and some of it will be examples and problems that you have to work with. Okay? But some of them will be proofs. So you should expect that probably by Wednesday next week. And if you have any questions, let me know.
Will we have homework assignment there as well?
And your homework due on?
Wednesday.
I hope that I'll get that graded fairly quickly and get it back to you so you can use it. Okay. Is there anything else of me?
Well, since I'm going to be on vacation next week, is it okay if I take a picture of it and email that to you?
Yes. Yes. You're talking about the homework?
Yes.
That's fine. Yeah, I'll be able to print that off. Okay, thank you very much for your time and patience. I think that's enough.
Thank you for clarifying. Thank you.
Well, I mean, I hope it was helpful.